Coefficient of determination and standard error of the estimate by myself, Marcus, and Jakob. So terminology. The residual plot constitutes both x values and y values, and together it forms the residual plot. Prediction interval. The interval estimate of a predicted value of y when the regression equation is used and a specific x value is given. The coefficient of determination is the measure of variation of the dependent variable that is explained by the regression line and the independent variable, and it is denoted r to the second power. Standard error of the estimate. Standard deviation of the observed y values. The explained variation is the variation picked from the predicted y values denoted SSE. Unexplained variation is the vertical distance between the predicted value and the observed value. Total variation is the sum of the unexplained and explained variation denoted SST. Y hat is a predicted value of the dependent variable, which is denoted Y. And Y bar is the mean value. So for real world applications, the concept of the coefficient of determination and standard error of the estimate can be applied in various ways and in any field in which gauging the correlation between two variables may be productive. For example, if I wanted to figure out if the pH level of the soil a plant was grown in has any correlation with the growth rate of the plant, I could use the coefficient of determination and standard error of the estimate to determine that.
How this can apply to mathematics and statistics. In mathematics, the coefficient of determination is used to determine probability and test various hypotheses. More specifically, it is a measure of the accuracy in which a statistical model can make a prediction. The standard error of the estimate is a measurement of the average deviation between errors in a dataset, usually a regression model. Some example problems. In this section, we will go over some example problems utilizing coefficient of determination and the standard error of the estimate. Example problem 1. Given a simple linear regression model with an r-squared value of 0.75 and a standard error of the estimate of 5,000, calculate the coefficient of determination, r-squared. We know r-squared is equal to 1 minus the sum of squared errors divided by the total sum of squares, where SSE, the sum of squared errors, and TSS is the total sum of squares. Since we know r-squared is equal to 0.75, we can rewrite the problem to solve for the total sum of squares. The total sum of squares is equal to 1 minus r-squared times the standard sum of error, the sum of squared errors squared divided by r-squared. We plug in the values. 1 minus 0.75 times 5,000 squared divided by 0.75 is equal to 8,333,333.33. The solution, the total sum of squares is equal to 8,333,333.33. Example problem 2. If you have a data set of 20 observations and after fitting a regression model, you find that the sum of squared errors is 400 and the total sum of squares is 800. Calculate the r-squared value. We know r-squared is equal to 1 minus SSE divided by TSS. We plug in the values. R-squared is equal to 1 minus 400 divided by 800 is equal to 0.5. Solution, r-squared is equal to 0.5. Suppose you have conducted a multiple linear... Example problem 3. Suppose you have conducted a multiple linear regression analysis with 3 predictor variables, x1, x2, and x3, to predict a response variable, y. After fitting the model, you obtain a coefficient of determination, r-squared, of 0.85. If the total sum of squares, TSS, is 1,500, calculate the standard error of the estimate, SEE. We know r-squared is equal to 1 minus SSE divided by SST. Since we have r-squared and SST, let's rewrite to solve for SSE. SSE is equal to 1 minus r-squared times SST. Plug in our values. 1 minus 0.85 times 1,500 is equal to 225. The solution, SST, is equal to 225. Real-world application. The concept of coefficient of determination and standard error of the estimate can be applied in various ways, among them measuring data in experiments similar to the video above. This will be shown in example problem 4. You conduct an experiment to study the relationship between soil pH levels and the growth of a specific type of plant. You measured the height of plants after a fixed period and recorded the pH levels of the soil for each plant. The data set includes the pH levels and corresponding plant heights. Our given data, the soil pH levels 5 to 7. Corresponding plant heights is 10, 12, 15, 18, and 20. We can use the given data to fit a linear regression model where the soil levels, the pH, are the independent variable x and the plant heights are the dependent variable y. Using this, we can determine how linear the progression of the data is and how relevant the pH of the soil is to plant growth. Okay, to solve this problem, first we need to find the correlation coefficient r squared. We know r squared is equal to 1 minus SSE divided by SST, but since we don't have SSE, and SST, we'll have to calculate them using the mean plant heights, y bar, the observed plant heights, which we'll call yi, and the predicted plant heights, which we'll call yi hat. Y bar is equal to 10 plus 12 plus 15 plus 18 plus 20 divided by 5 is equal to 15. Yi hat is equal to the intercept plus the slope of x is equal to negative 16.2, which is the intercept, and 5.2, which is the slope, times x is equal to yi hat. Yi hat 1, meaning the yi hat of x1, of the first x value that we have, is equal to negative 16.2 plus 5.2 times 5. Y hat 2 is equal to negative 16.2 plus 5.2 times 5.5, because 5.5 is our second x value, etc., etc., etc. And we do the same for each x value. The SSE, which is the sum of yi minus yi hat squared, meaning we're going to do all of our 5 yi and yi hat values. We are going to sum those up. So we have 10 minus negative 16.2 plus 5.2 times 5 squared, and plus 12 minus negative 16.2 plus 5.2 times 5.5 squared, etc., etc., etc. SST is the sum of yi minus y bar squared, which we're going to do the same process. 10 minus 15 squared, 12 minus 15 squared, etc., etc., etc. We sum those and then divide them by the amount of values we have, which is in this case 5. So now that we've defined everything, let's plug and chug. R squared is equal to SSE divided by SSE divided by SST. SSE is equal to 10 minus 7 squared plus 12 minus 10.6 squared plus 15 minus 14.2 squared plus 18 minus 7.8 squared plus 20 minus 21.4 squared is equal to 13.6. SST is equal to 10 minus 15 squared plus 12 minus 15 squared plus 15 minus 15 squared plus 18 minus 15 squared plus 20 minus 15 squared is equal to 68. R squared is equal to 13.6 divided by 68 is equal to 0.2. So we have R squared value of 0.2. Interpreting the results from problem 4. Because R squared is 0.2, that means the pH of the soil is 20% related to the height of the plants, meaning it accounts for 20% of the increase in plant height. Because of this, we can conclude that the pH of the soil does not have a large effect on the growth of the plants, concluding our experiment.